I'm ready to start. So, good afternoon, everybody. Welcome to the Midlands Branch Pipeline Industries Guild first presentation of 2021. It's great to see so many people dialing in. We really appreciate what a challenging time it is. Time seems even more precious than normal now, and we're conscious that everybody's got a lot on, so we will be running to time today, and we've got three fantastic presentations lined up, all focusing on leakage in water. We're starting with Mikal Willmott from Severn Trent. He's going to be talking about large diameter metering. Then we're going to go to Alan Cunningham, who's going to talk to us about a research project on behalf of UKWIR on the impact of leakage levels on detected and reported leaks. And then Jo Parker from Watershed Associates is going to present on a project she's been working on with Severn Trent Water, looking at leakage detection teams striving for the gold standard. So we've got three great presentations. I'm going to ask everybody, if you've got any questions, please raise them through the chat function as we go through the presentations. What I'll do is I'll collate them all, and then at the end we can sort of treat it like a panel, and we can I can sort of field the questions so all presenters get a chance to answer your questions. If we don't have time for any, please still post them and we'll get a response out to you as soon as we can. Thank you very much for joining us, and I'm going to hand over to Mikal. If you take over the screen with your presentation, then we can get started. Excellent, thank you.
Thank you. Rachel, can you just confirm we can see the screen?
We're seeing it with your slide. Oh, that's it. That's better.
There we go. Brilliant. Thank you. Really grateful for the opportunity to be able to speak to the Pipe Industries Guild today. I know I am the warm-up act for Alan and for Jo, who are coming later, but I'm grateful to be able to spend a few moments with you today and just to share some of the things that I've learned about large diameter metering over the last 15 years or thereabouts. I'd like to first of all kind of thank the organisations and many friends and colleagues who have helped me over the years to help me understand a little bit more about large diameter metering and such likes. So Peter Drucker has taught us that you can't manage what you don't measure, and metering is very important to measuring the amount of flow that's going in our systems and to helping us with leakage and with reducing leakage and such like. And so large diameter metering plays a really important role in this. And where do we find these large diameter meters? We find them at abstraction points. We find them often at the end of treatment works with the distribution input meter. We find them on trunk mains and transmission mains, and also sometimes at our service reservoirs. We find them at the inlets and the outlets of our service reservoirs. In the UK, there's a variety of technologies that we use to meter our large mains. And often these meters, when they're put in, they're installed for a very long period of time. So this meter on the left-hand side here was put in about 30 years ago, and it has had 500 billion litres of water pass through it in that time. An amazing amount of water if you think about it. And again, it's really important that when we install our large meters, that we do install them correctly, because they are there for a long, long period of time. There are four technologies we primarily use in the UK. Electromagnetic meters, which are by far the most popular meter that's been installed in the UK water industry on larger mains. And these are fairly easy to install if, and that's a big if you can turn off the main. So 30 years ago, when lots of these were installed, or 20 years ago, we used to write letters to the customers. We used to tell them that they were going to go without water for a few hours, and we would basically drain down the main and we would install an electromagnetic meter, which generally are the best meters to install. As time goes forward, and as we become better at customer service within the water market, we decide that we can't actually turn off the water to the customers. So we now look at retrofit meters that we can install. The most popular retrofit meter in the UK is the clamp-on ultrasonic meters, where you put transducers on the sides of the mains, and these transducers, they send ultrasound pulses to each other. And the length of time it takes from a pulse to get from one transmitter or from one transducer to another, you can then infer a flow rate. Then there's other technologies that can be used, such as wetted ultrasonic meters. And again, these are like clamp-ons, but they actually go into the main, slightly into the main, and also insertion probes that can have single or multi-points. And these little sensors, these little points, are able to detect the velocity and work out what the flow rate in the main is. So today I want to share 10 principles that are really useful for us to understand how to install and how to maintain large diameter meters. It's fair to say that these are general principles, and in some situations, these principles don't always hold up, but in most cases, they do. So the first principle is that flow distortions travel further in larger mains than in smaller mains. If we look on the left-hand side here, we look in the ideal world scenario, we have water going down a main. Now, water goes at different velocities, at different speeds. In the ideal world, what we have in the middle of the main is we have the highest velocity, the quicker water. And then towards the edge of the main, because of the friction of the pipe wall, we have slower water, slower velocity. And this is what meters kind of are designed for. But what happens is, as water goes through fittings, as it goes around bends, flow becomes distorted. And what we can see is that high velocity can be sent to one side of the main. And also in larger mains, we can get swirl. And we see skewed profiles. These skewed profiles can make it more difficult for meters to read more accurately. And in larger mains, because the ratio between the pipe wall and between the area is greater, these distortions go on longer, much longer than we get in smaller mains. So NEL, the National Engineering Lab, just based outside Glasgow in Scotland, has said swirl can take over 100 pipe diameters to decay. In fact, there have been cases where swirl has persisted for over 500 pipe diameters before the profile returns to exceptionally close to ideal. And a really good case study was given in 2007 in the American Waterworks Association Journal, where Dick Finesse went down to Brazil. He went to a pump station that had a 48-inch pipe coming out of the pump station, and he showed that 200 diameters downstream from this pump, from this last disturbance, you could still get a distorted flow profile. And so swirl was still persisting. So in larger mains, flow distortions do travel longer. Principle 2. For electromagnetic meters, get at least 5 diameters downstream from the last disturbance. A question I often get is, how close to a disturbance can we install a meter? Testing that was carried out by Evaluation International on a 500mm rig tested an EMAG meter, and it put it 0 diameters down from the last disturbance. In other words, it got a disturbance, maybe a bend or maybe a gate valve that was partly shut, and it put the meter directly behind that disturbance. And we see relatively high errors. They then moved that EMAG meter to 5 diameters downstream, so 2,500 mils, and we see that the errors got smaller. They then moved it 10 diameters downstream, so 5,000 mils from the last disturbance, and the errors got very, very tiny bit smaller. So my takeaway here is that if you put your meter at 0 diameters, you could have relatively large errors, but for an EMAG meter, just get 5 diameters downstream and the errors will reduce greatly. If you go to 10 diameters, you'll get some marginal benefits, but they are very, very marginal. For ultrasonic meters, it's a little bit more complicated, the picture. Again, some testing done here by IMP Services, and they tested on a 500mm rig, and they tested a number of ultrasonic meters. And basically, these black and red and blue bands were how close the meter was to the last disturbance. And what we see generally is, as you move away from the disturbance, you get lower errors. WRC did something slightly similar. However, their results were a little bit more varied on a 300mm main. And this is because it comes down with ultrasonics, a little bit of probability. You may get lucky where you might just get a sweet spot, and that may only be 2 diameters downstream from the disturbance, or you may get unlucky and 10 diameters downstream, you get a really bad placement. But having looked at the results and having looked at many results over the years, and having spoken to quite a number of my peers and those who are experienced in metering, our view is, with the game of probabilities, the best thing you can do in all likelihood to reduce errors on ultrasonic clamp-on meters is to try to get that meter as far away from the disturbance, whether it be 10 diameters or 20 diameters or 30 diameters or 50 diameters. Try to get it as far away from the disturbance as you can. Something that will help out ultrasonic meters is putting on more paths, more transducers. The more transducers you have, the more paths you can have, and you get a better sample, a better representation of what's happening in the main, and you get more accurate and more precise metering and results. The other thing that's really important for ultrasonic metering is to take into account the wall thickness and also the temperature of the water. So the temperature of the water affects the sound, the speed of sound in water. Sorry, the temperature of the water affects how quickly sound travels through water. And now sometimes you may get a few mains right next to each other and you think all the mains are exactly the same, but they're not. We went to a treatment works earlier this year where all the mains were the same size, they were all the same material, and they were all installed at the same time. And as we looked at the pipe wall thickness from one main to another, we saw a pipe wall thickness of 35 mils, of 13 mils, and then 38 mils. We also saw the temperature of the water changed, and we think this is because one of the pipes was getting water from towards the top of the river, and one was abstracting water lower down in the river. So what I'm saying here is when we put it on ultrasonic meters, don't just use default values, or just don't think that the main next to it is exactly like the main that you're about to install on. It's not. We need to do accurate measurements to lower errors. Principle 6 is accuracy is best when velocity is ½ meter per second or greater. There's lots of testing that has proven this, but as you get to, and I'm just using an example of an EMAG test that was done up in Scotland with Evaluation International, but I've got similar data for ultrasonics and such like. As you get to a higher velocity, accuracy does improve, but once you get to about 0.5 or thereabouts, the increase or the change is really marginal, if anything at all. When you have really, really low velocities, you can get some really big errors. So I would suggest, if I was writing a design manual, I would say you want at least 0.5 meters per second or greater for your velocity. And this next one was an absolute mind blow when I saw these results that came out just a few years ago. Evaluation International, I work quite closely with them on these tests, did like-for-like tests on a 250 mil main and a 500 mil main, used the same technology, the same manufacturers, but just did like-for-like tests. And what we saw was that errors on a 250 mil main were far lower than on a 500 mil main. And this may come back to the hydraulics we spoke about earlier. In fact, all these tests you see here on the 250 mil main were less than 1% in error, whereas on the 500 mil main, we go up to 3, 4, 5, even 6% errors, or close to 6% errors on the really low velocities. And so what this teaches me, or what this is really useful for, is if I'm designing a main and or designing an installation, do I put 2 smaller meters in on 2 mains, or do I do one huge main and have one larger meter? It's better to do smaller installations where possible. This also explains sometimes when we're trying to balance trunk mains, where we may have a large meter at one end and a smaller meter at another, and they don't seem to align. This evidence seems to suggest that smaller meters tend to be more accurate. Principle 8, very quickly. Some people come to me and say, look, there's an error with the problem. We've got a problem with the meter. We think it's an error. What's wrong with it? And quite often it's actually the SCADA data. So again, testing done by a UK water company a few years ago did 54 random tests where they looked at the SCADA data, and they then used a data logger, then compared the data. And on 31 occasions, the difference between the data logger and the SCADA data, and they were both attached to the same meter, gave us a 1% or greater error. And on 6 occasions, the difference was 5% or greater. Principle 9 is to remember that meter installation is a skilled job. Meters really need to be handled with care. They need to be loved. They need to be seen as something that is fragile. How we move them down into the chamber or into the pit should be done with great care. Also for ultrasonic meters, where we put the transducers really matters, and millimeters matter. I've got this photo here from Flowly Meter Verification, who do some work for Severn Trent, and they use lasers to ensure that their transducers are set up and aligned perfectly. It's really important that people who install meters are very fussy people, that they are very particular, and they want to do a very good job. Precision is absolutely key when installing meters. And principle 10 is the principle of keep learning. We've learned lots about large diameter metering in the last few years, and we've still got lots to learn. There's lots of information on metering in general out on the web, and there's some really good information there. The Crone Academy is an online academy that you can use that has some absolutely brilliant resources. The IWA water loss webinar that was presented last year, again, is a place that you can go to. And again, there's some really good examples there. Utah State University have produced quite a few items that you can go on to, and quite a few academic papers, which are well worth reading. And kind of in that spirit of learning, I'd like to present also today a new research project that's just been launched today by the National Engineering Lab in association with ARUP and WRC and Utah State University. And the purpose of this research, and I've been involved in the last 9 months, kind of getting it to this stage, kind of working as a technical support on that, is to produce a worldwide best practice for the design, installation, and verification guide for large diameter meters. There isn't one at the minute that's out there that is based on comprehensive evidence, and so this project seeks to do that. And in doing so, it will be doing lots of meter testing. It will be taking meters that have been in the ground for a long time and taking them out to see how accurate they are. There's going to be modeling of what happens with electromagnetic fields, which we think can sometimes affect the accuracy of meters. It's a really big project. It's looking at about £1.5 million the funding will come in for. And it's a project that I've had opportunity to speak to people in different countries around the world about and communicate about. We did some market research, and we think there's interest from about 16 different countries already. I'm speaking to some people in the UK, and there's interest from UK water companies as well in helping fund this project. And it's a project that will help us understand how best to install large diameter meters so we get the best results from them. And I'm really grateful for the endorsement that the Pipelines Industry Guild has given this. So Norman Howe, the CEO, in a letter from last year said, this research project will give much needed guidance of the design, installation, maintenance and verification of large diameter meters. The knowledge generated by the project will be of invaluable use for the pipeline industry. In addition to the Pipeline Industry Guild, there's been other endorsers of this project as well. And it's a project that we're really excited about. So in conclusion, there's lots of things that we've learned over the last few years. There's lots of things that if we follow through, if we act on them, we'll be able to get better water balances, we'll be able to reduce leakage, we'll be better asset management, we'll be able to do better installations. But going forwards, there's still a lot more that we need to learn. And thank you for your time this afternoon.
Okay, thank you very much, Michael. I think it's my presentation next, isn't it? So I'll just share my screen. Okay, can someone just let me know that they can see my screen share okay?
Yeah, good.
Excellent. Thanks then, everybody. So just to introduce myself first, for those of you who don't know me, I'm Alan Cunningham, subject matter expert at Ovarro, with too many years than I care to remember in leakage strategy. And I'm here today to talk about a project that we carried out for UK Water Industry Research Limited, or UKWIR, on the impact of reductions in leakage levels on the frequencies of reported and detected leak repairs. So just, I know we've got, some of you will be more familiar with UKWIR, but others potentially less so. So UKWIR was established in 1993 to provide single voice research for the UK water industry. The idea is that it shapes and leads the future research agenda for the industry, looks at what the current and future challenges are for the industry, and how to respond to those with research work. The membership is the UK water companies, and effectively they act as steering groups for individual research projects to guide the work undertaken. And the idea is that this is high value collaborative research, both nationally in the UK and internationally, with some support from other countries where appropriate, and to provide robust and reliable evidence on behalf of the water companies, to enable informed interaction with regulators and benefit, well, both the water companies as businesses, but also the industry as a whole, as we look to improve for the future. And in particular, as part of that, encouraging the sharing of best practice and continuous improvement as we go forward. So this project ran from July 18 to July 2019, and the work was carried out by Ovarro with myself as kind of the leader from our side, and managed by Joe Parker, who will be speaking to us in a minute on behalf of UKWIR, with Andrew Oakes of Thames Water representing the water industry and their views on the steering group, together with representatives of many of the other UK and Ireland water companies. So the objectives of the project were to look at the impact of reducing leakage levels on the average frequencies of mains bursts and other identified leaks on supply pipes, communication pipes, and so on. Look at the proportion of those bursts and leaks that are reported by the public, and compared with those that are detected by active leakage control activity by the water companies. Look at the size of identified leaks, both reported and detected, and the run times of those identified leaks. So how long before the water companies become aware and then need to go out and detect those leaks. And part of the kind of the background for this project is that, as most of you are probably aware, the regulators are requesting quite significant drops in leakage from the water companies over the next 5-year asset management period, and typically of the order of 15% reductions and even more in some cases. And this project is to help understand, as the water companies look to drive down leakage, what is going to be the impact on the numbers of leaks that are being found and needing to be repaired, with all of the costs and disruption that repair of leaks results in. So firstly, if we start by thinking about the life of a leak. So initially there will be a hole in the pipe that will start leaking. Gradually that leak might get bigger over time, and eventually it will get to a level where it might become visible at the surface and reported. But most leaks will run for a significant amount of time that they are not visible to the general public, and therefore there's a need to increasingly go out and detect more and more of those leaks, repair them earlier in that cycle, and thereby drive down leakage. So the approach for the project was to collect data and carry out some initial analysis, and in particular to look for areas within water companies where leakage has been reduced substantially in the past. And this was a bit of an issue for the project, in that whilst in the kind of the 2020 to 2025 periods, the water companies are being actively incentivized by the regulators to drive down leakage. And there's kind of limited examples where there's been real substantial and sustained reductions in leakage in recent years. And also it's quite difficult to sort of compare any two areas, because obviously you've got the counterfactual of, well, what would have happened if we hadn't driven down the leakage in that area. So that necessitated a bit of a change to the approach, to move towards a kind of a cohort analysis and look at district meter areas. So areas of the network where leakage has either been falling, where it's been rising, or where it's been relatively stable. Look at trying to develop a kind of pipe level model of leakage, and the numbers of identified leaks based on the pipe characteristics, and carry out analysis of key performance indicators, and a model as a very kind of high company type level, based on a wide range of characteristics of the network and leakage in those companies. So in terms of the results, the initial analysis showed that there was an increase in reported leaks during summer, which is kind of explained by obviously drier ground, wet areas that represent leaks being more obvious, and an increase in detected leaks during winter, when the ground's wet, so leaks rising to the surface are less obvious. And more leaks are breaking out because of cold weather. It showed that it's difficult to kind of separate out the various influences, such as increased customer awareness of leakage, particularly if you've got kind of dry weather and messaging about the need to save water, then customers might be more likely to report leaks, depending on the facilities that water companies have put in place around reporting leaks on the website. That obviously encourages more reporting. With some indications that smaller leaks, such as on stop taps, were increasing as the water companies attempted to drive down leakage in particular areas. So then when we started to kind of cohort the different areas, we found that the areas that we were looking at in terms of whether leakage had been rising, falling, or stable were kind of scattered geographically, and it wasn't kind of reflecting changes in consumption, or more generally, there were a few differences in the overall characteristics. So the main differences between the cohorts were whether leakage in those areas had been rising, falling, or stable. And what we were saying when we were comparing those different cohorts was that there was no real evidence of changes in reported leak numbers according to what was happening to leakage in those areas. But where areas had increasing leakage, there were actually kind of higher numbers of detected leaks. So what was happening there was that actually, as companies were seeing areas with increasing leakage, they were putting more and more effort in and trying to drive that leakage down, but they were finding that they were detecting higher numbers of leaks, even though leakage was going up. When we compared that with the results of other modelling, we were seeing that the kind of the minimum night flow or the leakage doesn't really have much of an impact on the level of reported leaks, but where you've got higher leakage, you see more detected leaks. So obviously companies are putting in effort into these areas, trying to drive leakage down and finding more leaks. And similarly with the key performance indicator analysis, the reported leaks were kind of broadly constant, and not really affected by the leakage level or the amount of active leakage control effort that the companies were putting in. But where leakage was higher, you were seeing more detected leaks, and obviously as you increase the detection effort, then more leaks were being found. This is kind of what we were seeing from modelling results perspective. So on the x-axis, we're looking at what happens if you increase the amount of active leakage control you're putting into an area, and on the y-axis the amount of additional leaks that are being identified. And what you find is that the more and more effort you put into areas, you don't really affect the numbers of reported leaks that much as might be expected, but you detect more and more leaks, but with diminishing returns. So this was obviously sort of some unexpected recommendations that needed quite careful thinking through. But one thing that was coming through clearly as part of the project was there was limited evidence to support one kind of theory that's been proposed in the past, that as leakage gets reduced, you get fewer reported leaks coming through because leaks are being detected more quickly, and that kind of offsets your increase in detection. And the kind of the differences in DMA behaviour were relevant to the relationships we were seeing between the leakage levels and the numbers of identified leaks. But what became interesting was that stable DMAs tended to be suburban areas, so they weren't the kind of the rural areas where there might be one large leak that's quite difficult to detect because the network spread out over a large area, and also the kind of the city centre areas with lots of leaks breaking out and potentially rising and then falling as detection effort is put in. There was one particular concern that was raised by the water companies, which was that if they start trying to reduce leakage, then they might detect more mains bursts, and that's one of the performance commitments that they're assessed on, because obviously mains bursts is something that we want to avoid. So that was one of the things that was kind of coming out of the project, was if you put more detection in, then you might see a slight increase in the mains bursts, but actually most of the additional leaks that you were detecting were on the smaller assets, the stop taps or the kind of communication pipes and supply pipes to customers' homes. There's one point here that I think most of the water companies should have taken away, which is we had difficulties in efficiently collating the data sources to analyse leakage levels and identify leaks. And those are what companies need if they're going to manage this in their own circumstances. So companies need to be able to make sure that they can get the information that leakage strategy managers need to analyse what's happening with leakage and analyse that efficiently and identify patterns, because well, there's a variety of teams that need access to those data. It's not just the leakage strategy team; it's also kind of the asset management team. Operations and strategy might be separate, so that access needs to be available. And also the key performance indicators data set that we used demonstrated the benefit of collating that data across the industry. So in terms of the recommendations that were coming out of the projects, we were recommending that water companies should factor the costs of additional leak repairs into the costs associated with reducing leakage when they're budgeting. And they should also monitor the leak repair counts that they're observing to ensure that those leakage reduction costs are being budgeted accurately. The water companies should focus on the well-established principles of leakage management to achieve reductions. So obviously, general good leakage practice, flow data monitoring, and good equipment, etc., etc. Then the water companies should collate the data with kind of governance procedures applied to that, and in particular providing access to those who need access to the data for analysis, and look to ensure that kind of cross-company data sets like the key performance indicator data set are maintained, and that definitions are agreed consistently to aid cross comparison for the benefit of all. In terms of the kind of the benefits arising from the project, it provided a view on the future numbers of detected and reported repair numbers. The findings support the companies in understanding what the costs and benefits of leakage reduction activity through active leakage control are, and supports comparing the cost and benefits for other approaches to meeting their performance commitments. So the project was very much focused on kind of find and fix approach to leakage reduction. Obviously, there are other approaches that can be taken around pressure management, renewals, etc., and this will help the kind of cost and benefits to be compared and ensure a holistic approach to leakage economics modelling and network management. It showed the value of data collection and collation and data management, and it kind of develops an understanding of DMA performance, and in particular why some areas are easier to manage than others for the network. And that is my last slide. So I think we're almost kind of bang on time. So I'll stop sharing and hand over to Joe for the final presentation. Thank you, Rob. Thank you for listening.
Hi, well, my presentation follows on quite well from Alan's. As you'll see, there are several parallels with what he talked about. And the presentation that I'm talking about relates to a project that was run in Severn Trent, and in fact is still running. A lot of you will know the Severn Trent area, but this shows a few metrics and gives the details of where it is. But I think the key thing for Severn Trent is that it's an area which covers both very dense urban locations, Birmingham, Nottingham, Leicester, but also it goes right over to the Welsh border, Gloucestershire, and some very rural areas as well. The project was initiated, again, you've heard from Alan about the requirement to reduce leakage, and but also up until a couple of years ago, Severn Trent outsourced their active leakage control, and they felt that that wasn't necessarily achieving the best results. So they decided to bring it in-house, particularly because in their business plan that they submitted for the current asset management period, set very tough targets for leakage, but there would be financial gains if they met them. So they felt they needed to have good control over those targets. So they introduced a new structure with 16 in-house teams for leakage control. Generally, those teams were had 2 teams to a county. There are a couple of areas, well, central area with Birmingham had 3 teams, and Staffordshire just has a single team. And in their recruitment, they were very much looking for people, the people capabilities, and felt that you could train the technical side. This meant that you had a very wide range of experience, people from in-house and outside, people from repair and maintenance, and from leakage contractors, and So people had different strengths and weaknesses, but Severn Trent didn't necessarily know where those strengths and weaknesses were. In addition, they were losing some staff to neighbouring water companies and wanted to ensure that the training and support given to those teams was the best possible support that they could have. And they were very keen that any work with the teams was aligned with the Severn Trent values and objectives, that the teams should have courage and tackle, which they'd need, could tackle these tough targets. They should take pride in their work, to encourage people to ask why they're doing things like they are, and to take care over the resource and their work as well. The project built on some Severn Trent initiatives. I've mentioned they were bringing back active leakage control in-house. Myself, as the co-author of this presentation, Jon Daniels, had worked with Severn Trent before on a project, Skilled by Choice, where there'd been detailed competencies assessment of all the frontline and first line supervisors working in distribution. And following that, everyone had had some coaching feedback. So this was building on that competency assessment. And then Severn Trent had done a lot of work looking at DMAs and trying to improve the network to make it easier to run and easier to find leaks. There were also some initiatives outside of the company which were relevant. Mikal Willmott, who spoke first, and myself had both been to a leakage conference in South Africa run by the Waterloss specialist group of the IWA. And in South Africa, they had a very wide range of performances, from Cape Town, for instance, where they had very sophisticated systems and had very good levels of leakage, to other areas where very little had been done. There were huge losses from the network. And so South Africa had encouraged some active benchmarking to ensure that the less well-performing areas could see what could be done and would learn from the good performers. There's a system of benchmarking set up by the IWA, IBNET, and Alan's just mentioned that there is data collected by the Water UK Leakage Network, quite a wide range of data that people can look at. And although the water companies are anonymized, they are able to identify what their data is and how they compare. And then finally, there was an UKWIR project which looked at active leakage control efficiency, which actually ran parallel to the project that Alan's just talked about, and was also managed by Ovarro. It's called Measuring the Efficiency of Active Leakage Control. And that looked at parameters that you might want to measure and how best to measure active leakage control. So the Gold Standard Leakage initiative that myself and Jon Daniels managed took account of all of those previous projects. And we set out to look at performance measures that weren't just looking at inputs, for instance, time spent in the field or the amount of money spent. It didn't just look at outputs, for instance, such as night lines or leakage lost per connection per period of time. But it also looked at how things were done. processes that we used. And the other thing about our performance measurement was that we didn't just look at technical measures. Severn Trent had spent a lot of effort trying to recruit the right sort of people who would demonstrate the right behaviours. So we looked at those behaviours, and we also looked at the operating environment and the network capability of the different areas, because comparing performance between Shropshire and central Birmingham does have its problems. And with leakage performance management, as I have found directly as a leakage manager in the past, there's always an excuse as to why you are maybe not performing quite as well as some of the others. So we did collect some of the data via a questionnaire that looked at different levels of performance. And we actually grouped all this information into 10 different categories, some of which were, if you like, fixed underlying factors, such as the network condition or the operability, some of which were straightforward technical performance, and some of which were these less technical issues. And we divided each of these areas into a 5-point scale. And to get away from the red, amber, green that is so often used, as far as we were concerned, they were all capable. And so we term them green, which is the lowest level, then blue, bronze, silver, and gold. And the target was to bring everyone up to the same gold standard. We carried out a detailed analysis of the work that was being done and identified areas that were stronger and weaker than others. And we also tried to identify areas that had similarities with things like density of properties, length of mains, the age of the mains, the geology, was there more clay, and then topography. We originally thought of showing the data either via a radar plot or some sort of table, but actually we found the visual approach didn't really add an awful lot. What we did do was have initially face-to-face meetings, but that was knocked on the head fairly rapidly. So we had Zoom meetings with the leakage managers or other video conferencing, or sometimes it wasn't possible to have the video connection. But we went through their performance and how they compared with other people, asked them about any anomalies we found, and really asked them to validate what we were saying about their strengths and weaknesses. And the interesting thing was that we did pick up areas that had clear similarities, but those areas didn't necessarily have similar performance. We could roughly group them into rural, suburban, and urban. As I said, this project is ongoing, and our final report will be based on that sort of approach. One of the things we found was that the operability of the DMAs was very closely linked to efficiency. And the good thing was that the teams were being encouraged to own their areas. Each leakage technician worked in a specific area, and they were encouraged to identify any issues with the DMAs. Not all the information was as readily available as some, and in other cases where you had data available from two different sources, it didn't always agree. So there was a lot of requirement for data cleansing. But the managers gave us very positive feedback, such that the ones who were sort of being considered further down the line were clamoring, when are we going to be looked at, and when can we have our discussion? And the other thing was that we picked up all sorts of different strengths, and the managers, some had done a lot of work on pressure management themselves, some had done a huge amount of work on, for instance, operability. One or two had developed very strong relationships with local authorities, which facilitated both their access and the repair and maintenance team's access. So there are all these different strengths that we found. And the funny thing was, the weaknesses were virtually the same. So there was a great opportunity for pairing people so that they could mentor the managers who were not as strong in those areas. And this analysis has meant that we've been able to have a very robust review of what training is needed a couple of years now down the line from introducing the in-house approach. And looking at the underlying characteristics of the areas has eliminated the excuses, so that managers are owning their performance and are very keen to have the training that we're looking at. And this will also allow robust targets to be developed for the future, which again, the teams can really buy into. And we have these mentors for the future. And some of the things that really has taken, it's really a bit different with this project is that, as I said, we've looked at the process by which people achieve the outputs, not just what they put in. We have looked at the background information and the behaviours, and we've had these facilitated discussions. So the results haven't just been imposed on people. We've discussed it with them, taking a short-term view of leakage, because so often people can go for short-term benefits, which doesn't necessarily put companies in a good position for the future. So a rather rapid run through this project, but it leaves a little bit of time for some discussions.
Jo, Michael and Alan, thank you very much for that presentation. We've got a few questions. So Alan, if you turn your screen on as well, we will start with, I think this one is directed at Michael. Are mag flow meters really the preferred and most reliable solution? Is there any evidence to support this? The cost of civil works and disruption outage for mag flows is often prohibitive. What comparison can you make with the NIVUS under pressure solution, especially on required accuracy levels?
Okay, so I think generally, yes, the EMAG meter is the best meter that we can get. You can put it in very difficult circumstances and it performs very well. And we've tested quite a number. And we've also tested, with the help of Evaluation International, the NIVUS flow meter, the under pressure one. I think you're talking about the wetted ultrasonic here. And when you had 8 paths, so that's 16 transducers, we found that it did perform as good as an electromagnetic meter on there. And so we have used the NIVUS in certain places in Severn Trent. We haven't used 8 paths, but that's a lot of paths. But in some places where we know we've had fairly good hydraulics, we have put in the NIVUS. So again, there will be some situations where the NIVUS or other manufacturers like that will be the best solution. But if you have the opportunity to turn off the main, which I know is becoming less and less likely these days, the EMAG meter, I think it's hard to beat.
Thank you, Michael. Alan, one for you. Comment being very interesting. Do you think that the low levels of leakage you looked at represent the low levels that are needed, i.e. were they 20% below where they would normally be given the AMP6 methodologies?
Yes, thanks, Jo, for the question. I think the project highlighted that there's actually kind of limited examples in the country where companies have driven down leakage to the kinds of levels that will be needed by 2025. So what companies are going to need to do is to monitor over the next 5-year period to see how the leakage and repair numbers progress in practice, and also try and come up with approaches that prioritise large leaks for repair to achieve the targets for the lowest overall cost, because obviously the more and more small leaks that get put through for repair is going to increase the costs overall.
Great, thank you, Alan. Joe, one for you. This looks like a good model to apply in other areas. Do you know of other areas being assessed in a similar way?
I'm not sure if they mean other areas activities or other areas water companies. As far as other activities go, I think there is some merit in this sort of input, process, output review of performance, particularly where you have you're trying to encourage the right behaviours as well as the right sort of technical approach. As far as other areas, water companies, not that I'm aware of, although obviously the Ovarro UKWIR project did look at similar approach, but very much a sort of modelling and frontier analysis of performance. But a lot of the parameters we found to be important were judged to be important within the UKWIR project as well.
Thank you, Joe. And I'm going to just slip in one last question to the whole panel. What would you recommend as best approach to take to quickly detect leak in a rural, smallish diameter plastic PE pipes? I've got in brackets, sometimes these PE pipes may have been slip lined with a CI pipe.
Shall I go first? Oh.
Yeah.
Okay. Well, hi, Trevor. Thanks for the question. So, I mean, what I'd be suggesting here is a hydrophone correlating logger. The reason for that is that the hydrophone listens in the water rather than along the pipe, so that avoids some of the noise transmission issues that you get with plastic pipes. But I probably need to declare a potential conflict of interest here, because one of the examples is the Enigma 3 IQ that we supply.
Well, the good thing is I can actually support Alan's comment. There has been some good performance with hydrophones within the Severn Trent teams, some of them. Again, the interesting thing is some teams have tried them out, other teams haven't. So it's an area where the champions for that approach can maybe support the other people who haven't used it to take that on board. There are also sort of multi-factor monitoring systems that are coming in, and these may be successful. I know they've been used to look at PE pipe in other countries.
Yep, I can concur with all of that. The hydrophones are really powerful in plastic mains. The other thing to look forward to, if this is kind of becoming a long-term thing and you want to monitor that DMA, is looking at the possibility of dynamic pressure monitoring. So you put out a number of pressure monitors and you see what the changes in those pressures, again, can alert you to an area of interest.
Great, thank you everybody. I'm very conscious of time. I know we've got a lot of people still logged in. So what we'll do is we'll take the questions that haven't been answered, we'll take those offline, get responses to them and upload them to the Guild website. Can I say a massive thank you to Mikal, Alan and Joe. We really appreciate the time that you've spent doing this, and judging by the interaction we've had, logins and questions, it's been really worthwhile. So thank you very much. I wish everyone a safe January, and we will be back soon with more webinars.
Thank you.
Thank you.
Thanks, everybody.
Bye-bye.